Welcome. In this video, I'm going to go over the practice problems found at the end of the chapter for sections 4.4 and 4.5. Starting with question 15, it says carbon and silicon belong to the same group of the periodic table. Describe and compare three features of the structure and bonding in the three carbon allotropes, diamond, graphite, and C60 or fullerene. So if I just write down, I've got diamond, graphite, it's the stuff they put in your pencils, and then C60 or fullerene. They all have covalent bonds. But the difference is that graphite and C60 just have what we'd call typical covalent bonds or molecular covalent bonds, whereas diamond actually has a giant covalent bond. And then they all have LDF forces holding them together. Graphite and fullerene actually have delocalized electrons. So they're semiconductors, whereas diamonds have no delocalized electrons. As far as the structure, like I said, diamonds are a giant covalent, so it's a very tight 3D structure. Whereas graphite is more of a two-dimensional, it's in sheets. That's why it works so well as pencil lead. And then the C60 is like a soccer ball shape. It's alternating pentagons and hexagons, just like a soccer ball. Bond angles are going to be 120 for diamond. They're going to be around 109. Oops, I'm sorry, it's going to be 120 for graphite because that's the two-dimensional one. And it's going to be around 109, 109.5 for diamonds. And for the C60, it's going to be 109 to 120 depending upon which of those spheres you're in, a hexagon or a pentagon. The number of atoms attached to each one, graphite and fullerene attached to 3 other carbon atoms. Oops, thought I had it there. Whereas diamond attaches to 4. This is a question that I wouldn't be surprised that IB on the big test asks you some things about the allotropes. They're not going to ask you this extensive of a question. So if you can remember a couple differences, you might pick up a point or two. Question B wants to know about, let's go back and see here. Let me just pause this and I'll clear this so we can go back. So part B wants to know the structure and bonding in SiO2. And SiO2 is unusual because instead of forming double bonds with each oxygen, it's really more, the SiO2 is more like a formula unit that what really happens is each silicon bonds to 4 oxygen and each oxygen bonds to 2 silicon. So it makes this much larger structure of, I've got Si with 2 oxygen here and then another silicon here, but then it's also got 2 more oxygen down here, but then they're bonded to another silicon. So you can see how this goes on endlessly, much like diamond does, and it forms this giant, very tight structure. So since there's covalent bonds between every atom in the structure, this is going to be held much tighter together, and it's going to be a very solid substance. Think sand and quartz when you think about SiO2, the stuff they use in glass. Whereas CO2 has individual molecules, and even though they're polar bonds, they're nonpolar molecules because they're a linear shape, so it's going to have very low LDF forces and going to be a gas at room temperature. And C, describe the bonding within the carbon monoxide molecule. I think what they're getting at here is for you to recognize that because there's a triple bond and oxygen and carbon each have a lone pair, not only is it a triple bond, but it's a triple bond with one dative bond in it, because the only way that triple bond forms is for oxygen to donate both electrons for the third bond in the triple bond. So number 16, they give you the name and the formula, fortunately, for these, since we haven't done organic yet. But if you remember our mini organic drawing lesson, this is going to, methoxymethane is going to look like this. So even though there's some polarity with the oxygen here, this is a mostly nonpolar molecule. There's slight polarity with the oxygen, but not a highly polar bond, whereas with the C2CH5OH, I've got the very polar hydrogen bond down here, and then the nonpolar end. So this is going to have a much lower boiling point, because it's less polar. And this is going to be much higher because it has a very polar hydrogen bond in it. Number 17, CCl2F2 was used as a coolant in refrigerators. It's been discontinued due to concerns about destruction of the ozone. So A says, draw the Lewis electron dot structure of CCl2F2. And so when you draw this, you end up with carbon and 2 chlorine and 2 fluorine. So the question is, do the chlorine and fluorine alternate, or are they side by side? And based on the information we were given, we don't know. So either way would be acceptable. And then B wants to know, predict the shape of the molecule and the bond angles. It's going to be tetrahedral. And that means the bond angle is going to be 109.5 because there are no lone pair. And then C, is it a polar or nonpolar molecule? So this is B here, this is A here. It's going to be nonpolar. And the reason why is the polar bonds, or the charge, is evenly spread, or evenly distributed, we say, around the molecule. So even though there's polar bonds, it'll be a nonpolar molecule. And then D, explain what is meant by resonance with reference to Lewis electron structures of ozone 3. So if you draw ozone, you're going to have a double bond and a single bond. So 3 lone pair, 1 lone pair, and 2 lone pair. And the resonance is the idea that the double bond resonates or moves back and forth between both possible positions. So I'll say between both oxygen sites. And when they measure it, it actually measures around 1.5. So there's good evidence that it's moving. And they now think that that extra pair of electrons that forms the double bond actually just kind of acts like delocalized electrons and kind of spreads itself across both areas, never truly in either place. And then E says, contrast and compare the bonds in O2 and O3 and suggest why ozone may be more easily broken down in the stratosphere. So O2 is going to be a double bond like so. And because this is a true double bond, this is going to be shorter and stronger bond and harder to break, where this is going to be a slightly longer and weaker bond in the ozone, making it more susceptible to breaking down. High energy UV light hitting it. Number 18, Vesper theory can be used to predict the shape of molecules. Explain the application of Vesper theory in the following, including in your answers full Lewis dot structures. They remind you have to put your lone pair on, the name of the shape of the molecule, and the bond angles present. So 18A1, pH3 is going to have a lone pair and the 3 hydrogen pushed down. So that's going to be trigonal pyramidal. And because it has a tetrahedral electron domain shape, it would be 109.5 with no lone pair. And because there's one lone pair, I can expect it to be around 107. H2O is going to be bent. It too has a tetrahedral electron domain, but because there's two lone pair, I would expect the bond angle to be around 105. C2H6 is going to have just a single bond and then the 3 hydrogen. And I mentioned this in class that you have to look at, when I look at this, I can look at this carbon, I can look at this carbon and the 4 things attached to it, or I can look at the right-hand carbon and the 4 things attached. But I don't consider both carbon at the same time. So from the perspective for each carbon, it's tetrahedral. So for each center atom, for each carbon, it has a tetrahedral shape around it. And that means the bond angle is 109.5. And then number 4, CH3CHO. Drawing this in the order that it appears, I've got CH3, CH, and then the O is going to have to be double bonded there. So this one, the left one is going to be tetrahedral, the left carbon. It's 109.5 because it looks very much like the ones up above. But my carbon on the right is only bonded to 3 things with no lone pair. So that one, the right carbon, I would consider trigonal planar with a bond angle of 120. And then B wants to know only one of the molecules is able to form intermolecular hydrogen bonding. State which molecule this is and describe the features it possesses which makes it possible. So the only one that can form hydrogen bonding, it has to be hydrogen bonding with fluorine, oxygen, or nitrogen. So the only one is H2O. And the features that make it possible is the fact that it has a positive end by the oxygen, a very negative end, a positive end by the hydrogen, a very negative end by the oxygen. So then other oxygen or other water molecules, I will see the oxygen attracted toward the hydrogens of a neighboring molecule, and the hydrogens, we call it a head-to-tail fashion. The hydrogens attract the oxygens of their neighbor, the oxygens attract the hydrogens of their neighbor. Number 19, properties in elements can often be predicted from the knowledge of their bonding, deduced from their positions on the periodic table. So A1 says, describe the bonding in potassium metal. It's a metallic bond. So that means the positive nuclei line up and the negative delocalized electrons move freely throughout that structure. And it gives me a lattice of positive cations with 1 valence electron free floating among there per potassium atom. If it were a group 2 like a calcium, then I'd have 2 valence electrons and a slightly stronger metallic bond. And then 2 says, state 3 properties of potassium, explain each in terms of the bonding described. It's a good conductor. And that's because the electrons are free to move. It's malleable and ductile, because when you hit it, you're not going to disrupt the positive lattice, because the lattice isn't alternating positive and negative like ionic bonds are. Then it's what we call a non-directional bond, so you're not going to disrupt that by hitting it with a hammer. It also has a high melting point. because of the strength between the cations and the delocalized electrons. And then it's also got luster, or what we call shiny, because the electrons reflect light. Because the electrons are moving, they have that tendency to reflect light. Part B says describe the bonding in fluorine gas. Fluorine gas has very different bonding because fluorine is the most electronegative of the nonmetals. So it single bonds with itself and holds itself together quite tightly. But it only has LDF, or London dispersion forces, in it because it's just the one bond. So it's held by the attraction between the nucleus of one fluorine for the shared pair and the nucleus of the other fluorine for the shared pair. And I don't know if it really asked for any properties or not. Oh, yeah, it did. Let me just see my question up here. And it says, name and describe the forces present in the liquid state, because as a gas, it won't have intermolecular forces. But as a liquid, it's going to have London dispersion forces because it's a true polar bond, which is why it typically exists as a gas. C wants to know, with reference to their electron configurations, describe how, can't quite see this question, describe how potassium and fluorine combine to form potassium fluoride. So with their configurations, potassium is large, so it has low ionization energy, so it gives up its electron easily. Fluorine, on the other hand, is tiny with a high electronegativity, and it is happy to take that electron. Got the strength to do that. So we form an ionic bond where one electron is transferred from potassium to fluorine. And then D says, explain why sodium fluoride does not conduct electricity in the solid state, but is a conductor in its molten form. Well, in its solid state, we have Na plus alternating with F minus, and they're held rigidly together by this attraction, the electrostatic attraction between the positive and negatives. So there's not freedom for those ions to move and conduct electricity. In the liquid state, though, as the very polar water molecule spreads out the sodium and the fluorine, the individual ions would be free to move, making them good conductors at that point. In number 20, I've already written in the information here because we've seen these bonds several times. Sketch and state the names of the shapes of the following molecules. So I have SiH4. That's going to be tetrahedral since it's just 4 hydrogens single bonded to the silicon. But the pH3 is going to be trigonal pyramidal since it has a lone pair attached to it. And then B wants to know, state the bond angle in each. Well, tetrahedral is going to be 109.5 because all 4 electron domains are bonding pairs, and they take up equal space since they all are attracted. Each bonding pair is attracted by 2 nuclei holding them in place. But the pH3 has 4 in its electron domain, but only 3 bonding pair. So that lone pair is free to crowd the 3 bonding pair, and that's what gives it its asymmetrical trigonal pyramidal shape and a bond angle of just 107. In number 21, again, this is a bit redundant from other problems we've done, but they want a Lewis electron structure of ammonia, state its shape and bond angles. So NH3 is going to have 1 lone pair, making it trigonal pyramidal with a 107-degree bond angle. B, predict and explain whether the ammonia molecule is polar. Yes, it is, because it has polar bonds with an asymmetrical shape, so that's going to form a dipole, or a positive and negative end. In fact, it's going to be a very strong polar bond, what we call a hydrogen bond, when it attracts itself with intermolecular forces. And then C, draw a Lewis electron dot structure of the ammonium ion, state its shape and bond angle. Well, this is going to be a true tetrahedral because now I've got a fourth hydrogen on there. So all 4 electron domains are bonding. So this would be tetrahedral with 109.5. And then D, state the name of the bond that forms between ammonia and the hydrogen ion and explain its formation. And what they're getting at is that you have NH3 with its lone pair, as I've shown here. And this lone pair then, I've got the hydrogen ion with no electrons. This hydrogen ion moves in and simply goes ahead and attaches itself to that lone pair. And it doesn't take any more energy for the nitrogen to have that lone pair or to be sharing that hydrogen. But it immediately changes the shape of it because now the lone pair no longer can exert a greater influence. It can no longer take up as much space because it's got the hydrogen and nitrogen nuclei holding it in place. And that's what D is asking about, is how the shape changes. And it's because there's 4 bonds on nitrogen in each case, but 4 bonding on the NH3 or on the NH4 versus there's 3 bonding and a lone pair on the NH3, and that's going to change the shape from trigonal pyramidal on NH3 to tetrahedral when that hydrogen attaches via a dative bond or coordinate covalent bond. And number 22, the structure of ethanoic acid is shown below, and we drew methanoic acid earlier in this problem set, so it should look similar to you. It says, comment on whether or not this representation is a Lewis electron dot structure, and your hint is that they include the word electron dot, so no, this isn't. There's no lone pair shown, and there would be if it were a true Lewis structure. And then predict the bond angles around each of the 2 carbon atoms. Well, the first carbon atom I see has this carbon, this hydrogen. It's got this shape there. It's got the 4 bonding pair to it. So that would be tetrahedral at 109.5. But my second one, this carbon has a carbon, an oxygen, and an oxygen attached. So this one's going to be trigonal planar. So as far as the bond angle, the first one's going to be 109.5 and considered tetrahedral, but the second one is going to be 120. So compare and contrast the bonds between the carbon atom and the 2 oxygen atoms. Well, the double bond is going to be shorter and stronger. And the single bond is going to be longer and weaker. And D says, when ethanoic acid ionizes, it loses a hydrogen ion and forms the ethanoate ion, CH3COOH. So you can see it's the H out on the end, the hydroxide that gets lost. And it says, explain why in this structure the carbon-oxygen bonds are different from either of the carbon-oxygen bonds in ethanoic acid. And the difference is that the bond can now resonate. And both are more like a 1.5 bond. Neither one's a true single bond, and neither one's a true double bond because that extra pair of electrons is free to resonate between them.